In this video, we finish the proof of the first isomorphism theorem for rings. And I want to start by reminding you that the theorem says that if we have phi as a ring homomorphism from R to S, and I is the kernel of phi, then the quotient ring R mod I is actually isomorphic to the image of phi. And we got started on the proof of this theorem in previous videos by defining a map pi from R mod I to phi of R, defined as pi of R plus I is just phi of R for every left coset R plus I inside the quotient ring R mod I. And in the previous videos, we showed that this map pi is first of all a well-defined function. And in the second video, we showed that this particular map pi is a ring homomorphism from R mod I to phi of R. And so all that we have to do now is we need to show that pi is onto and 1 to 1. Because if pi is both onto and 1 to 1, then pi will indeed be a ring isomorphism between the quotient ring R mod I and the image phi of R. And so the two rings will be isomorphic. So let's move on to doing this. So our first task, we will show pi going from R mod I to phi of R is an onto map. Now, in order to show something is onto, we have to pick something inside the target set. So we're going to let S be any element of phi of R, and we need to find an element inside of the domain of the function. In other words, we need to find a left coset, R plus I, such that pi of this left coset is indeed equal to our little s. This stuff here is our goal. Now, what do I know? Let's see. Since S is inside phi of R, that tells me there exists a little r inside ring R such that phi of little r is actually equal to S inside ring S. Now, since R is inside capital R, R plus I is a perfectly good element of the ring R mod I. And look at this. If I feed R plus I to pi, and I have to get my notation correct. So if I feed R plus I to pi, by the definition of pi, that's nothing more than phi of R. But phi of R is just S. And so this is the definition of pi. And this particular equality is because phi is onto, and S was chosen to be inside phi of R. But the net result of this is that this set of calculations implies that pi, taking R mod I to phi of R, is indeed onto the subring phi of R. Well, okay, what about 1 to 1? So we're now going to show that pi going from R mod I into phi of R is 1 to 1. Now I want to recall an important thing about ring homomorphisms. A ring homomorphism is known to be 1 to 1 if and only if its kernel is trivial. And what that means is that its kernel is equal to the set containing the zero element of the domain ring and nothing else. Well, let's see. If we apply this particular theorem to the situation at hand, we get the following important observation. Our map, our ring homomorphism, pi from R mod I to phi of R, is going to be 1-to-1 if and only if the kernel of pi turns out to be the singleton set containing the zero element of the domain ring, which happens to be R mod I. But I know what the zero element of R mod I is. That's just 0 in ring R plus the ideal I. And so our goal then is going to be show that the kernel of pi is actually nothing more than the left coset 0 plus I, that is the only left coset that gets sent to the zero element inside the target ring phi of R. So let's see, how do we go about doing that? Well, let's let R plus I be any element inside the kernel of pi. So what does that say? That says pi of R plus I is going to be equal to the zero element over in ring S, since pi takes R mod I into phi of R, but phi of R is a subring of S. And so the zero element in our subring phi of R is equal to the zero element in the ring S. But I also know something else. Pi of R plus I is just phi of R. So this particular equation here will imply that phi of R is equal to 0 inside ring S. Well, that says that R has to be an element of the kernel of phi. And the kernel of phi is actually equal to I. And so what does this say? This says that R plus I is actually the same thing as I, and that says that the R plus I is actually the same left coset as the 0 in R plus I. And this is basically by how left cosets work. And so the upshot of this is that the kernel of pi contains exactly one element, and that one element is indeed 0 plus I. And that says that pi is 1-to-1. Well, so what do we now have? In conclusion, in the last two videos plus this video, we have shown the following things. First of all, pi defined as a map from R mod I to phi of R given by pi of R plus I is equal to phi of R is, first of all, well defined. That was our first video. Second of all, pi is a ring homomorphism. Third, pi is onto phi of R. Fourth, pi is 1-to-1. Well, all of this says that pi is a ring isomorphism from the quotient ring R mod I to the image of phi. And that's enough to say that R mod I is isomorphic to the image of phi. And that completes the proof of the first isomorphism theorem. Before we end this video, there is one thing that I want to talk about, and that is a corollary. And the corollary is this. If phi is a ring homomorphism from R to S that is onto S, then it turns out that R mod I will actually be isomorphic to S itself. And the proof here is very easy. The proof is a one-liner. Since phi is onto S, the image of phi is equal to S, and so R mod I is known to be isomorphic to the image of R, but the image of R is equal to S, so R mod I is indeed isomorphic to S itself.